Suppose we'd like to analyze this circuit. And we look at it, and it looks pretty easy, right? We have a couple of resistors, and an inductor and a capacitor, and a voltage source and a switch. Certainly we know Ohm's law, so we know the voltage-current relationships across those resistors. And we know voltage-current relationships for inductors and capacitors. Certainly we know how to write Kirchhoff's voltage law around a loop. So let's say we write two loop equations there. In the end, we'll end up with two equations and two unknowns, but those equations will be differential equations. And so we might ask ourselves, well, what do we do next? Well, one of the tools we can use is the Laplace transform. The Laplace transform takes differential equations and converts them to algebraic equations. And here I've shown the definition here of the Laplace transform. And what it does is it introduces this new variable s. Okay, you take your function, you multiply it times this exponential, introducing this new variable s. There's some integration with respect to t, and the variable t drops out, and what we're left with is a new function in terms of s. And it's this new function in terms of s that we manipulate algebraically. We do all the manipulations we need, and at the end we do an inverse Laplace transform to get back to the time domain. Okay, so I'm going to show you how to get from here to the solutions that I have for this current and this current. So this current solution I sub L is shown right here, and this current solution I sub C is shown down here in terms of time. So obviously you don't see enough math here, step by step manipulation of math on this board. What I'm going to show you is just the key steps here in this video to keep it as short as possible, and then I'll have some links below at some point that shows some of the detailed step-by-step manipulations for those that may want to look at those. Okay, before we do any Laplace transform work on this circuit, let's take a look at initial conditions and steady state conditions though on this circuit. Let's assume that the right half of this circuit has no energy stored in it before we flip this switch. So at time equals, before time equals 0, there's no current flowing in this inductor. There's no voltage across the capacitor. At the instant we flip that switch, at exactly t equals 0, there's still no current in the inductor, and there's still no voltage across the capacitor. Just at that instant, though. Okay, and that's because it takes time to build up charge across the capacitor, and it takes time to build up the magnetic field and store energy in the inductor. Well, what that means is at time equals 0, this voltage appears entirely across this 1 ohm resistor, and we get a current of V amps passing around this left-hand loop. There's no current passing through here. And so I show at time equals 0, the current through this part, I sub L at 0 is 0. And the I through this capacitor here, right, around this loop, at 0 is equal to V amps. At time equals infinity, or as we head, so in the steady state as time goes on, the capacitor is charges up to its full potential, and the inductor, it stores as much energy as it's going to store, right? And so the inductor then starts behaving like a short circuit, and the capacitor starts behaving like an open circuit. So what that means is this voltage here then appears across this 5 ohms. And we get a current of V divided by 5 through the outer loop. Okay, and that's shown here as time goes to infinity. And there is no current flowing through this branch that's acting like an open circuit. So the current through the capacitor as time goes to infinity is 0. So the reason I show those is if you take and plug in 0 down here into these two equations, or if you take the limit of these two equations down here, as time goes to infinity, you will get these results here. So that's a good check. Okay. Now, it turns out we're not going to use this integral directly in practice. For circuits like this, there are tables out there already, or you may have already memorized some of the Laplace transforms that deal with circuit elements on an element by element by element basis. And so, for example, the Laplace transform for this voltage source, well, it's really the voltage here at this terminal, okay? For this step function of voltage where we go from 0 to V, that Laplace transform is V divided by S. Again, you can look that up in a table. The Laplace transform, this 1 ohm resistor is 1. It's 4 for this. It's 2 times S for this inductor and 4 over S for this capacitor. Now, if there were energy stored in the inductor and the capacitor before we flip that switch, then there would be additional, there'd be some additional terms here for the inductor and capacitor. But we're not going to handle that case here. We're just going to assume that there was no energy stored in those to begin with. Once we have our circuit elements labeled with their Laplace transform values here in red, we can just do our regular Kirchhoff's voltage law. So we can write a loop equation here and a loop equation here. And I've done that, and I've shown it here in matrix form. So for example, IL times 1, here is IL times 1, and IC times 1 plus 4 over S, okay, IC times 1, and IC times 4 over S equals V over S. That's the V over S in that loop. And you can do the same thing, a loop here, and you'll get this second equation here. So now that you have it in matrix form, what we can do is we can just solve for our unknowns IL and IC. And I've done that here. I've got the solution for IL and I've got the solution for IC. You can do that either doing an augmented matrix here with this piece of the matrix augmented with this column vector and do some row reduced echelon form work. Or you could use Cramer's rule. It's a 2 by 2, so not too bad. And there we have it. Essentially, we have the solution for I sub L and I sub C. The problem is it's in the S domain. We need to convert it back to the time domain because we don't really know what that means in the S domain, right? Okay, so the inverse Laplace transform. Okay, this is what all the rest of this is about. We need to get something here in the denominator, primarily, is what we're looking for, that in this case, that's first order in terms of the variable S. The way we're going to do that is we're going to use something called partial fraction expansion. If you're not familiar with that or you're a little rusty on that, there will be a link there showing you how the details of that. But essentially, we factor the denominator here into its multiplicative factors. Okay, that ends up being S, and then two complex factors here: S plus 3 minus I, the imaginary number I, right? S plus 3 plus I, and S plus 3 minus I. Okay, so if you stick this into the quadratic equation, for example, you'll get two complex roots. You'll get minus 3 plus I and minus 3 minus I as the roots. Okay. And then what we need to find is the coefficients A, B, and C using partial fractions. Again, if you don't know how to do that or you're a little rusty, go check out the link below and I'll work out this example. But here's the results of once we find A, B, and C. So A, for example, is V over 5. So this term becomes V over 5S. And over here again we have some sort of a complex number over a complex first order polynomial, right, factor, and the same thing here. Those we know how to do inverse Laplace transforms, and again there are tables for this, but when you do those inverse Laplace transforms, you end up with complex exponentials. Okay, e to the it plus e to the minus it divided by 2. Here's an e to the it minus e to the minus it divided by 2i. Okay, so this is where you need to be familiar with Euler's equation, Euler's identity equation, for that converts between complex exponentials and sines and cosines. If you're not familiar with that, again, I'll have a link there that just shows you what that is. But this e to the it plus e to the minus it over 2 equals cosine of t. It always equals cosine of t, okay? It's an identity, just like a regular trig identity or something like that. Here, e to the it minus e to the minus it divided by 2i is sine of t. And again, that's just an identity. Okay, so you have the solution, or at least the outline of a solution here. We have the I sub c in terms of S. You could take this I sub c and work through sort of the same steps here. You'll come up with this. That would be a good exercise to do on your own. And then, of course, once you have I sub c and I sub L, you can solve just about anything else in this circuit, voltages and currents. It's pretty simple. Okay, so that's Laplace transform.